So after example 5, that was the limiting reactant problem, where it was just a whole bunch of work. You guys are more than capable of doing it. It was just very scary because we haven't been doing math recently, and it was a big math problem and lots of stuff's involved. But you're fine. You can do this, okay? We can change the PV equals nRT equation to incorporate molar mass and density. So one very important use of the ideal gas law is the calculation of the molar mass from its measured density. To save some time, I'm just going to show you some things, and then I'm going to show you what the equation is. So density is mass over volume, which that equation is on the page 13 side with the gases, liquids, and solutions area. Okay? And molar mass, what are the units for molar mass? Grams per mole. So if you wanted to find moles, which we know from our PV equals nRT, moles is N, okay? Would you multiply by molar mass or would you divide by molar mass if you had grams?
Where are we at?
Divide. We would divide. So we would take the mass of our gas divided by the molar mass of our gas. Well, what we can do is we can replace in PV equals nRT, we can replace moles and volume with density and molar mass. If we divide the volume over, so it's the moles times R times T over volume, the N and the V would cancel if we would plug mass over molar mass in here. It all cancels away, just believe me. Then the equation would be the density, which is capital D density, times R times T over molar mass. So write this equation down because you may need to use it on a homework problem. Okay? So, and you could also rearrange it if you needed to solve for density, right? You could move everything over and get density by itself and solve for density that way too. So, for example 6, we're given a density of a gas is 1.50. Good? Okay. So we're given density, we're given that the pressure is 1.5 atmospheres at 25 degrees Celsius, and the density is 1.95 grams per liter. I forgot to mention, density should be in grams per liter for gases if you're going to plug it into that equation, just to make sure that everything still works itself out. And we want to calculate the molar mass of the gas. So I'm going to rearrange the equation from before, where I will have the molar mass is what everything equals to. So what you would do is you would multiply the molar mass up here, and you would do with what? With the pressure. Divide it. Yeah, so you just kind of switch places with the molar mass and the pressure. So it'll be the density times R times T over the pressure. Okay? So we have 1.95 grams per liter times R, which is the 0.08206, times, I didn't list out my stuff this time, I apologize. But do we plug in Celsius or do we change it? Got to change it to Kelvin. So 27 plus 273 would be 300 Kelvin.
Where did 0.08206 come from?
It's the R value in the ideal gas law, and it's on the page 13 side of the equation sheet. So you'll have that. You get to use this equation sheet on tests and quizzes, so that's why you have it, so you can learn where things are.
Wait, so
that's the R that we use for the ideal gas law, PV equals nRT. And then the 1.50 pressure goes on the bottom. So what do we get for the molar mass? 32.0. Did somebody else get that too?
32.0.
Okay, So now the 27 degrees Celsius we should round into 2 sig figs. So it'd just be 32. And what's the unit for molar mass? Grams per mole. On one of the free response questions last chapter, I think it said that you had to, for the answer key, it said you had to imply molar mass was needed. Some people solved for it, which is good. And on the AP exam, one of the multiple parts of a free response question might just be solving for molar mass like this, or just, adding it up from the periodic table. So just make sure that you label it so you get that point, okay? All right, we're almost there to the end of 3.4. So John Dalton did experiments with gases to propose his atomic theory. We have Dalton's atomic theory. 4 out of the 5 are still correct to this day. He summarized his observations from his work with gases that for a mixture of gases in a container, the total pressure is equal to the sum of the pressures that each gas would exert if it was alone. So Dalton's law of partial pressures says that the total pressure is equal to the pressures of the parts. Okay? Well, when we have this equation, and if we have our PV equals nRT, and we get pressure by itself, which would be nRT over V, then we could maybe have lots of different moles of all of our different types of gases. And then this could convert into where we would have our total pressure is equal to the mole of the first gas times RT over V plus the mole of the second gas times RT over V, etc., etc., etc. And this can be condensed down to help you, where the P total would be equal to the N total, so the total number of moles, each type of gas added together, times RT over V. Because in a certain situation, the temperature isn't going to change if it's just one condition. The R never changes, and the volume of the container won't change because all of the gases are mixing together inside that total volume. So that would be another way to use this equation. Example 7, what we're going to do is we have 2 different gases that are being added together, and we have to figure out partial pressures of each one, and then we'll find out total pressure. So instead of combining like this, since we do need to know in the next one each partial pressure as well, we're not going to use this equation. We'll use like each separate PV equals nRT and solve for each P separate. But in the event that you don't need to know the partial pressures for the answer, you could use this. Okay? So mixtures of helium and oxygen can be used in scuba diving tanks to help prevent the bends. For a particular dive, 46 liters of helium at 25 degrees Celsius and 1 atmosphere, and 12 liters of oxygen at 25 degrees Celsius and 1 atmosphere were pumped into a tank with a volume of 5 liters. Calculate the partial pressure of each gas and then the total pressure in the tank. Okay, so we have 2 different gases. We have helium, we have oxygen. Okay, well, for the helium, we know that we have 46 liters, which is a volume. We know that we have 25 degrees Celsius, which is a temperature. And we know we have 1 atmosphere, which is pressure. Then for the oxygen, we know that the volume of the oxygen pumped in is 12 liters. The temperature is also 25 degrees Celsius, and it is also 1 atmosphere because we are outside of the sea. Okay, so what the problem is saying is we have 2 separate containers of helium, or a separate container of helium and oxygen. It should be diatomic, sorry, my bad. And they're getting pumped into the same container. So when they're added together, the tank, when they're added together, has a volume of 5 liters. And we want to know the total pressure in the tank when they're added together. Okay, so eventually what we'll do is we will take, for the total, or for the tank, we need the partial pressure of helium plus the partial pressure of oxygen. So we will need to solve for each of these pressures when they've been added into the tank to do that. Okay, so the thing that doesn't change about each type of gas before it's pumped and after it's pumped, what's missing from our equation with the data that we have? Moles. So when we pump it into the tank, the moles are still the same. They're just compressed together now. So what we're going to do is we're going to solve for the moles of each of them. And then when we know the moles of each of them, then we put them into the tank. So we solve for the partial pressure inside the tank of each of them, and then we can find the total pressure. Okay? So we're first going to solve for the moles of each using the initial information. So we have 1 atmosphere times 46 liters is equal to the moles of N. Is it okay if, again, today I just put R to save some space, so you guys know what number to use? Okay. And then 298 Kelvin is the 25 degrees Celsius. If one person wants to do the oxygen to help speed up our process along, that might be good. And don't worry about rounding to significant figures yet, because we don't round until the very end of sig figs. So I kept like 3 to 4 sig figs on my numbers.
Really get
How I do what?
that. Like
How to solve it?
Yeah.
So it's from PV equals nRT. Well, this is the equation from yesterday. We had this in Chem 1, where pressure is atmospheres, volume is liters, moles, R is that 0.08206, and then temperature in Kelvin. So on mine, I'm not writing out the R value to save space, but it is that 0.028606.
Divide the.
So yeah, so we're just solving for N. Yeah, we're just solving for N. Did anybody get one of them? 1.881. Is that good? Okay. Did anybody do the oxygen? Four nine seven one. 07. 07. That's okay. Okay. So now that we have the moles of each of the gases, we need to find the partial pressure inside the tank. So we're going to use PV equals nRT again, still plugging in the moles separately for each of our 2 different problems. We're going to solve for pressure this time. And what is going to change? What number is going to be different than before? What's the volume of the tank? 5 liters. So the volume is going to be a different volume, but the temperature is going to be the same as before, because we didn't say that there's a new temperature, right? It just says that there's a new volume. So, yes, yeah, you could think about it that way. You could do, yep, you could divide over the V. So you could just do nRT over V. Yep, that's fine if you like to do that. And we're going to have to do this separate for both of them. We need it for the partial pressure of helium, and we need it for the partial pressure of oxygen. Do you guys want me to like write out all of the work? Yes. Okay. Is it okay if I just do the changed version of the equation? So we have for helium 1.881 times R times 298 divided by 5. And then for oxygen, it's 0.4907 times R times 298 over 5. For oxygen, I got 9.2 atmospheres. Somebody else get that? Yeah. Okay, and that's rounded to sig figs because this is one of the answers we need. And then oxygen, I got 2.4. Does anybody do oxygen? Not yet. What did you say? 2.4. Okay. Then the last thing that we need to do, because this was part of it, we needed to know the partial pressures of each one after they've been put into the tank. And then now we need the total pressure overall for both of them mixed together. So to find the total pressure of the tank, all we do is we add the two together. So is it okay if I erase over here to write this down? Yeah. Okay. So to find the P total, all we do is we take 9.2 plus 2.4, and that is 11.6 ATM. Now, if you were trying to do full, complete, significant figures, you could round that to 12 atmospheres because 2 sig figs technically, but if you're adding, the rule is you keep a decimal. You keep the same amount of decimals. So I would probably take either one. Or if I forgot and I was only thinking one way, if you argued it with me, I would take the other way too. For significant figures. Okay? So that's just another way that we could use it. So the ideal gas law equation can be used multiple times. You could use it multiple times within the same problem because you will have initial conditions and you'll have final conditions, and we're just assuming that the relationships stay the same between the pressures and the volumes, okay, and the temperatures. So the last equation that we have is a mole fraction, which a mole fraction can be defined as a ratio of the numbers of moles of a given component in a mixture to the total number of moles in the mixture. The best way to think about a mole fraction is it's like a percentage without multiplying by 100, basically, okay? So whatever the mole fraction is supposed to be about, then you would put that many moles, those moles on top, and then the total moles for the whole thing on the bottom. This ratio could also be used with pressure, and it also could be used with volume. So I think in the next problem we use pressures instead of moles, but it still works the same way, where just like when I'm figuring out your grade on the quiz, which I had graded yesterday and I forgot to show you, then I take the number of points you get over the total points possible, divide them, and that's what your average is. That's what your percentage is. So it's the same kind of thing as those. You take the part divided by the total possible, just like that. Okay? So for this problem, we have a partial pressure of oxygen observed to be 156 torr in air with a total pressure in the atmosphere of 400 743 torr. And we want to calculate the mole fraction of oxygen present. So it doesn't matter that these are torr because they're both torr, so the units are going to cancel out regardless. Okay, so to find the mole fraction of oxygen, we would take the pressure of oxygen, which is 156, over the total, 743, and we would just divide those, and that would be the answer.
Is that like a special sign, or is that just
It's a Greek letter chi, which is basically an X. So yeah, I made it a little fancy because it's technically a Greek letter, but it's okay if you don't. So I got 0.20210.
Yeah.
And mole fraction doesn't have a unit because the units just cancel each other out. And we didn't multiply by 100, so that's why it's not a percent. Okay? Not too bad, right? All right, one more example, and then we talk about graphs, and then we're done. We can do this, guys. We can do this. Yeah, just think if you were here yesterday, too.
That's all I'm saying.
Okay.
It's gonna be even worse that I wasn't, so now I'm gonna have to try to catch up on it. Really?
A sample of solid potassium chlorate was heated in a test tube and decomposed into potassium chloride and oxygen gas. Uh-oh. A chemical reaction happened. What do you think you're going to have to do? Write it out. Exactly. The oxygen produced was collected by displacement of water at 22 degrees Celsius at a total pressure of 754 torr. The volume of the gas collected was 0.65 liters. That's supposed to be a space. Apologize. It's not land. And the vapor pressure of water at 22 degrees Celsius is 21 torr. Calculate the partial pressure of oxygen in the gas collected and the mass of the potassium chlorate in the sample that was decomposed. Okay, so the reason why you are given this information about water, remember when we talked about vapor pressure, and when you have water in an enclosed space, some of the molecules will escape and become a pressure over, or a gas over the liquid. And so that does hold a factor into the total pressure of the whole system. So if we are collecting oxygen gas above water, then there is some water vapor pressure that we have to take into account, okay? So let's write our equation. I already told you at the bottom what potassium chlorate was. KClO3 breaks into potassium chloride. What's that going to be? Take a guess. KCl. And oxygen gas. So 2. So we, to balance this, put a 3 in front of the O2 and 2's in front of the others. Okay, so we know that we have a total pressure, P total, is 754 torr. We know the partial pressure of water, the vapor pressure of water, is 21 torr. That was given to us. We know that the temperature is 22 degrees Celsius. And we know that the volume of the gas collected is 0.650 land. Just kidding. It's liters. Okay. Am I missing anything? Any other numbers? I don't think so. Okay, we need to calculate the partial pressure of the oxygen. And we want to know the grams, the mass. Looks like that. Okay, the grams of potassium chlorate. All right. So one of them is really easy to do. The thing we're going to do first is really easy. What did I just tell you about Dalton's partial pressure law? What can we do? Yeah. So all the pressures add together to make the total. And the only two gases involved are water vapor, which we know, and oxygen gas. So to find the PO2, we're just going to subtract total minus water. Okay? So that's the first thing. I know, right? We're just going to take P total minus the P water to find the pressure of oxygen, which is the first thing we need to solve for. So that would be 754 minus 21, which is, I'm not looking at the right page, 733? 4?
Is that what we have to do for that?
Well, that's for the first part, to find, this one's this one right here. Yep. But we still need to use this to go on to there. Okay. So now that we have our partial pressure of the oxygen, we need to convert it to grams of the potassium chloride. Yesterday, when we did the stoichiometry, we used what thing where it's moles 1 over moles half? Mole ratio. So we have to convert our partial pressure of oxygen into moles so we can do a mole ratio. That's our next order of business. Okay? So we've already used these things, so we're not going to use those anymore. If we use these and we use the partial pressure of oxygen, could we find moles of oxygen? That's the next thing we're going to do. So we can't keep torr, though. We have to convert it to atmospheres. So if you look on the equation sheet, underneath the R's, it tells you what are we going to divide by? 760. .96? Okay. Because it has to be atmospheres because R has units with atmospheres in it. So we have to keep it correct. Okay, so then to solve for N, we're going to have our 0.964 atmospheres times
6.1.
6.1.
But it's 0 and 5 makes it 1.
Mine says
96447.
Did you not take 754 when you subtracted minus 21?
Never mind.
Okay.
I got it in there right broke.
Okay. And 22 plus 273 is 295. And when we're doing this right now, this is going to be moles of O2. So the moles of O2 are I got 0.0259. Yes? Okay. 257. Because I had the 0.5. I had the 0.5. What did you have? I used when I converted to Kelvin, I had the 0.15 on the end of the number. Then you guys didn't. So what is it? 257? Okay. That's why it's different. Okay. So at this point, we now have moles O2, and we need to switch it to be moles of KClO3. So now we're ready for our mole ratio. Moles 1 over moles half, so it's going to be 2 moles of KClO3 over 3 moles of O2. And now we can just keep going from here because what are we supposed to solve about KClO3? Grams. And if we have moles of it, then how do you get to grams? Molar mass. Yeah, we need the molar mass. So we're going to multiply by the molar mass of KClO3. Save us some time, it's 122.6. Okay? So then from there, now you can just take your 0.0257 times 2 divided by 3 times 122.6. And I'm going to let you guys tell me the answer. 2.07? 2.107. And to go back, the temperature was only 2 sig figs, so we would round it to be 2.1, which I guess that's what I got. So there you go.
Where's my calculator? How did you get 21 or 2.101 not 07?
Oh yeah, this is asking about the DSR.
Yeah, here's us at 0.07.
I just remember you wrote down originally.
You just kept the whole thing in your calculator? Yeah. Is that what you do, Evan?
No.
Oh. Maybe it's slightly different because I did just write a rounded number up versus keeping the whole number up. And so maybe that's where it gets a little off if you keep the number in your calculator or not. I usually, if I'm working it out on my paper, I'll write something down, but I'll keep it in my calculator when I'm solving. Okay, last but not least. I'll give you a sec to finish writing this stuff down. We just want to briefly discuss these 3 graphs that you have in your notes just so that we know how the relationships go between pressure, volume, and temperature. Okay? Really quickly, review Chem 1. Are we all good if I move on?
Yeah.
All right. So, Boyle's law is the gas law that relates pressure and volume. And these graphs help us to realize what the relationship is, basically, okay? If we graphed pressure versus volume, just as they went, we would have this go this way. I don't remember the math term right now because I'm not the math teacher. But what this is saying is that the pressure, it's 1/2 the pressure is equal to twice the volume because of the way that it is changing. Exponential. Thank you, all you high math kids. Thank you. But if we would take the volume versus the inverse of the pressure, we would have a straight line for our slope. So, does anybody want to guess? Is it directly or inversely proportional? It is inversely proportional. So basically, you need to remember that pressure and volume are inversely proportional. So that means that if one goes up, the other one goes down, right? In the same proportion of that. So that's what Boyle's law taught us in Chem 1, that they are opposites. Then for Charles' law, which is the other graph, Charles' law is temperature versus volume. So this graph has volume and temperature, no inverses, and there's straight lines for different types of gases. So do you think that's inverse or direct? Yep, temperature and pressure are directly proportional. So, a cheat way, proportional, sorry, I can't spell. A cheat way, if you think about the equation, PV equals nRT, if the 2 variables are on the same side of the equal sign, they are inversely proportional. So pressure and volume are on the same side of the equal, so they are inversely proportional. But if they're on opposite sides of the equal sign, like volume and temperature, opposite sides of the equal, they are directly proportional. So that's a quick and easy relationship for you to see, because remember, this is for everything. Okay, so that's the end of 2.4. Finally.